Elastic deformable models are an effective way to create realistic animation. Our framework is based on embedding an object in a control lattice and applying the finite element method. The simulated dynamics correspond to the shape and material properties of the embedded object. Nonlinear elasticity simulations, however, are computationally expensive and difficult to control. We control the model using a skeleton whose motion is dictated by an external source. To avoid the computational expense of enforcing the skeletal constraint using Lagrange multipliers, the bones of the skeleton coincide with edges of the control lattice. This allows the skeletal constraints to be implemented algebraically, which actually speeds up the simulation rather than slowing it down. For sufficiently complicated models, the nonlinear equations of elasticity cannot be solved interactively. A well-known simplification is to linearize the strain and thus the equations of motion. This is a good approximation when the deformation is small, but for large deformations, severe distortions occur. Our approach is based on the idea that the soft tissues of vertebrates do not typically undergo large deformations relative to nearby bones. We decompose the object into overlapping regions, each of which is associated with a bone. As long as we measure the deformation of each region relative to a nearby bone, the equations can be linearized without producing such severe distortions. Here we interactively construct a skeleton for a more complicated model, which takes just a few minutes. The user clicks on the object to create a joint, which can later be repositioned. The control lattice can be constructed interactively by an experienced user in a few hours. In this visualization, the internal structure of the control lattice is exposed. The object is decomposed into regions by assigning region weights to the vertices of the control lattice. The region weights are interpolated so that every point inside the control lattice is assigned to one or more regions. The object can now be animated by specifying the motion of the underlying skeleton. Treating bones as one-dimensional constraints offers a performance advantage, but it produces an unwanted side effect. The twisting of the flesh around the bone is not penalized by the physical equations. Notice how the gloves and feet rock back and forth unrealistically, which exacerbates the bloating due to strain linearization. We remedy this problem by adding a soft constraint that penalizes displacement in the neighborhood of the bones. The twisting is reduced to a realistic level, yet the object still appears flexible. We have also applied our framework to this cow model. Our calculations factor in varying material properties, so we can specify the cow to have firm horns and hooves, shown here in white, but soft flesh and ears. Notice how the ears move much more easily than the horns when the head shakes. Our formulation also includes moving position constraints, represented here by white spheres. These kinds of constraints are useful for deployment of such objects in video games and virtual environments. Our method operates directly within an iterative linear system solver, adding very little extra simulation time. When a coarse mesh is not detailed enough to produce convincing interactions, we can adapt the basis in order to produce a more detailed solution in areas of high deformation. In this example, green spheres represent the original coarse coefficients, and blue spheres represent detailed coefficients that have been introduced in areas of high deformation. The linear simulation on the right is very fast, but the head is badly distorted. Our method is as fast as the linear simulation, but looks quite similar to the nonlinear version. This animation was simulated interactively at about 100 frames per second on a desktop PC. There is very little warping due to linearization of the equations, yet it runs about 30 times faster than the fully nonlinear simulation.